Welcome to this presentation on thermodynamics. In this topic, we'll learn how energy changes during chemical reactions and how these changes help us predict whether reactions are likely to occur. Scope and purpose of thermodynamics in chemistry, standard conditions, and key enthalpy definitions. Thermodynamics is the study of energy transfers during physical and chemical processes. In chemistry, we mainly focus on heat energy transferred between a reaction and its surroundings. The system is the chemicals involved in the reaction. The surroundings include everything outside the reaction, such as the container and the air. Energy is transferred between the system and its surroundings. Enthalpy, represented by the symbol H, is the heat energy stored in a system at constant pressure. We cannot measure enthalpy directly, but we can measure changes in enthalpy. Enthalpy change, or delta H, is the difference in energy between the products and reactants. It tells us whether energy has been released or absorbed during a reaction. Standard conditions are defined as a temperature of 298 K, a pressure of 100 kilopascals, and solutions at a concentration of 1 mole dm cubed. All standard enthalpy changes are measured relative to these conditions and are given the symbol H degree. The standard enthalpy of formation, H degree F, is the enthalpy change when 1 mole of a compound is formed from its elements in their standard states. The standard enthalpy of atomization, H degree At, is the enthalpy change when 1 mole of gaseous atoms is formed from an element in its standard state, and it is always endothermic. The first ionization energy is the enthalpy change when 1 mole of electrons is removed from 1 mole of gaseous atoms to form 1 mole of gaseous 1+ ions. Electron affinity is the enthalpy change when 1 mole of electrons is added to 1 mole of gaseous atoms. The first electron affinity is usually exothermic, whereas the second is endothermic due to electron-electron repulsion. Exothermic and endothermic reactions and energy profiles, Hess's law and indirect enthalpy calculations. Exothermic reactions release heat to the surroundings. They have a negative enthalpy change because the products have less energy than the reactants. Endothermic reactions absorb heat from the surroundings. They have a positive enthalpy change because the products contain more energy than the reactants. Energy profile diagrams show the energy changes during a reaction. They include the activation energy and the overall enthalpy change. Activation energy is the minimum amount of energy needed for a reaction to start. Even exothermic reactions need activation energy before they can proceed. Hess's law states that the total enthalpy change for a reaction is the same regardless of the route taken. This allows us to calculate values that cannot be measured directly. Hess cycles use known enthalpy values, such as formation or combustion data, to calculate unknown enthalpy changes by following different reaction pathways. Born-Haber cycles and lattice enthalpy, enthalpy of hydration and enthalpy of solution. Born-Haber cycles are an application of Hess's law used to calculate lattice enthalpies of ionic compounds. A lattice enthalpy is the enthalpy change when 1 mole of an ionic compound is formed from its gaseous ions, lattice formation enthalpy, or when 1 mole of an ionic solid is separated into gaseous ions, lattice dissociation enthalpy. A typical Born-Haber cycle includes several steps: atomization of the elements, ionization energies of the metal, electron affinities of the nonmetal, and the enthalpy of formation of the ionic compound. By applying Hess's law, these known values are combined to calculate the unknown lattice enthalpy. The enthalpy of hydration is defined as the enthalpy change when 1 mole of gaseous ions is dissolved in water to form 1 mole of aqueous ions under standard conditions. Hydration enthalpies are always negative because energy is released when ions interact with polar water molecules. The enthalpy of solution, H degree Sol, is the enthalpy change when 1 mole of an ionic solid dissolves in water to form an infinitely dilute solution. This process can be endothermic or exothermic depending on the balance between lattice dissociation enthalpy and hydration enthalpy. The relationship is given by H degree Sol equals lattice dissociation enthalpy plus sum of hydration enthalpies. Entropy as disorder and energy dispersal, Gibbs free energy and reaction feasibility. Entropy, symbol S, is a measure of disorder or energy dispersal within a system. Entropy increases when a substance changes from solid to liquid to gas, or when the number of moles of gas increases. Standard entropy values, S degree, are given in data tables and have units of J K to the power of 1 mol to the power of 1. Unlike enthalpy of formation, the entropy of elements in their standard states is not zero. Reactions producing gaseous products from solids typically have positive entropy changes. Conversely, Reactions that reduce the number of gas molecules usually have negative entropy changes. Gibbs free energy combines enthalpy and entropy into a single value that predicts whether a reaction is thermodynamically feasible. The Gibbs equation is G equals HTS, where G and H are in Kj mol to the power of 1, S is in Kj K to the power of 1 mol to the power of 1, and T is the temperature in Kelvin. A reaction is feasible when G is negative. For reactions with negative H and positive S, G is always negative, meaning the reaction is feasible at all temperatures. For reactions with positive H and negative S, the reaction is never feasible. When H and S have the same sign, feasibility depends on temperature. Common exam mistakes and how to avoid them. Key takeaways from thermodynamics. Enthalpy and Gibbs free energy values must be in Kj mol to the power of 1, while entropy values are usually given in J K to the power of 1 mol to the power of 1 and must be converted before use. Temperature must always be in Kelvin, not degrees Celsius. In Born-Haber cycles, confusion between lattice formation and dissociation enthalpy is particularly common. In summary, thermodynamics helps us understand energy changes in chemical reactions. Key ideas include enthalpy, entropy, Hess's law, bond enthalpies, and Gibbs free energy. These concepts are essential for success in A-level chemistry. Thank you for watching.